I really don't you.
No, how about we do after lesson 13?
Okay. I think it started, hopefully.
We're recording all the food science
Let's
people.
finish up 3.1 lesson. Okay, we left off talking about this very special number. I feel like you guys didn't quite get as excited as you should because this is a really important number in math. Probably second most popular after pi. The weird thing about this, Euler, sometimes they're pronounced Euler's number. I say Euler's. Is that it doesn't really like come from geometry like pi and a lot of the other like special like math. Numbers come from something that you can like prove or visualize with shapes and geometry, and this one doesn't. So this one's kind of cool. It comes more and it's used more in like calculus. I introduced you to like that limit notation of where it kind of comes from. But what you need to know is that this irrational number that occurs a lot in exponential growth and decay. So we call this our natural base. It's kind of like our perfect base for a lot of like application problems as well when we're talking about exponential growth and decay. When we graph this or write it as a function, that's just called our natural exponential function. Here's what it looks like, but we're going to go through and graph it together by just using a table and then practicing using the E button in our calculator as well. So you will need your grapher.
There's an E button in our calculator?
Yes, sir.
There's an F and a G and a B and a C too?
Yeah.
Why?
What?
There's literally every letter of the alphabet.
Normal letters.
Oh, you can use those to like store numbers on your calculator.
Oh.
I'll show you how to do that when you take calculus. Okay, so we're just gonna start by making a table, and then we'll use transformations to graph these other two because it looks like just a couple reflections. So it says graph, and then state the domain and range. So we're just gonna stick with our classic -2, -1, 0, 1, 2. Remember, domain for exponential is all real, so there's no restrictions for what I can or cannot plug into x. Okay, I gotta pull my graphing calculator quick while you guys do this.
I think I did it.
I found the button.
For you.
Did you? Yeah.
Oh,
It's right here.
Yeah, I just used the one over here.
There's one over there?
Yeah.
Where?
It should be like a little, there's actually two little italicized E buttons.
On the
You
divide button.
want to use the one that has like to the power of x.
Oh, you used the wrong one.
Oh yeah, I did show you this measure.
Are you sure? Here, I'll use this one too.
Okay, so you're looking for this button right here. The one that has e to the power of x. It should be right above the LN button. So you're gonna hit second LN to get that e to the x, and it automatically creates it as an exponential like term almost because it's used so much in exponential growth and decay. That's our natural base. So it automatically has a button. Hey, we know you're probably doing something exponential here, so we're just gonna do e to the power of -2. All right, obviously this is irrational, so we're going to have to just kind of round here. I just rounded to 2 decimal places for sake of, graphing 0.14.
Can we put it in like so Y and we'll make a table for us or not?
Yep. Yeah, you could do that. We could enter it into here. Second, e to the x. Oops. Hit my ink on accident. E to the x. And you can go to the table. -2, -1, 0. 1, 2. You could do that as well. Nice. But know where the E button is and how to use it. Okay. So by either looking at the table or crunching all those numbers, we got 0.37. Anything to the power of 0?
1.
1. Same with E. E to the power of 1 is about, there's that irrational number, the 2.718281828, ... so 2.72. E squared, 7.39. Okay, so let's graph this. Right, 7. Obviously, like I said, these are irrational numbers, so we're just approximating here. And we can see this does hold that same shape of an exponential curve that we talked about yesterday. Will this be growth or decay? Growth. It's increasing, and that base, that natural base, is in between 2 and 3, obviously that's greater than 1, so that makes sense that we have an exponential growth here. So it makes this kind of like a special number. And we talk about this in calculus a lot, is that e to the first, let me write it like this. E to the first, we have that irrational number that never ends. It's approximately here. It's the same value that if you were to find the area under this curve to the x-axis, and this is something we do a lot in calculus, is we calculate like this area under the curve and we connect it to like applications and like distance and stuff like that. But if you find this area under the curve, it is that same irrational number as what e is. Okay, that's what another kind of like special thing about this number is. Even though this goes on forever, there's an asymptote here. But if you were to like calculate all of this area underneath this curve, it is e exactly the 2.7 the same as this point on the graph. It's kind of cool. That's another characteristic. Yeah, it is neat. Okay, so here again, in all seriousness, if you didn't know how to graph this, you can make a table, but let's use transformations to make it easier. This is a reflection over which axis? Y. When it's just to the x, it's actually the y. Those horizontal ones are those ones that are just the x are backwards from what you think. So let's just take all those points we found. Obviously, all the y coordinates are now just going to become, or all the x coordinates are now going to become negative. The y coordinates are going to stay the same. Start with your key point, still right there on the y-axis, and then just reflect everything. So 2.7, 7.39. We'll come back to domain and range. Now I have exponential decay. And that's how we actually classify growth or decay with natural base functions, is if the exponent is positive or negative, because the base is always going to be e with the natural base function. It's always e. So when we're looking at, hey, is this an exponential growth or decay, we look at if the exponent is positive or negative. And again, connecting that transformations, we just know that it's reflected it. All right. Here, negative outside, that's reflection over the x-axis. And the graph kind of gave that away for you. So I'll go back to your key point there, 0, 1. That's going to now be at 0, negative 1. 1e, 2.72. That's going to become 1, negative 2.72. And then we have that 7.39. There we have those ones pretty close to the y-axis there. Okay. All right.
Growth, right? Because it's like still going.
It's technically decreasing if you read this left to right. So it's decay. Yep, that question. Do you guys remember what our domain is for exponential growth and decay? All reals, yep. All right, range, because we have that horizontal asymptote at y equals 0, it would just be 0, and then everything positive, 0 to infinity, parenthesis around both of those. Same thing on number 2, that didn't affect my range at all by reflecting it over the y-axis. However, number 3, negative infinity to 0. Listing negative infinity first, because that's technically a smaller value. Sometimes you guys flip those around. Okay. That's what our natural exponential function looks like. So again, what makes this a natural is we have that natural base e. So if you're ever wondering if it's going to be growth or decay, we kind of have to look at the exponent. As long as it's positive, it will be growth. As long as it's negative, it will be decay. Okay, we're going to do some more of these fun puzzle ones. Now, the nice thing about e is it's not a variable, okay? It's not a variable. It's a constant. It's a number, like pi. Pi is not a variable. Pi is a number. But it holds a lot of similar properties as like a variable, such as like exponent properties. So if you have, you don't have to write this down, just look up here. If you have e squared times e to the first, that is the same as e to the third, okay? So it almost like holds a lot of same properties that you're used to doing with variables, but it is a number. It's an irrational number. It's a constant. Okay, so just like before, we're kind of solving these exponential equations, and we talked about using just a little bit of like logic here. That if I have some base that's the same on both sides of the equation, and they're equal to each other, these powers obviously have to also be equal to each other. Okay? So I have my natural base e on both sides. 1's raised to 3x minus 2, 1's raised to the 7. So obviously those would have to be the same, meaning x would have to be 3. And you could just solve up a little, or set up a little equation and algebraically solve for that. Next one, very similar. The exponents have to be the same, meaning x would have to be -1. All right. 3 is similar, where I have the natural base e on both sides. So I'm going to set the powers equal to each other. The only difference here is I have a quadratic equation that I'm going to have to solve. So I'm going to try and factor it. If it doesn't factor, I'll use a quadratic formula. But this one factors. All right, so set it equal to 0. I'll quick do my AC method while you guys factor this. -24, add up to 5 would be 8 to -3. Okay, I got this to factor. 3x plus 4, 2x minus 1. Meaning x could be -4/3 and positive 1/2. Yep. Okay, we got 2 possible solutions for that one. Oh, let's zoom in here a little. Ooh, sloppy handwriting. Okay. The next one, the only difference is I have like kind of 2 terms on the left-hand side of my equation there. So I'm going to need to use some exponent properties. And I just mentioned that e holds a lot of same properties as if that were like an x, or even like a number, like 2. So when I have a power to a power, which that's what they're showing you right here, what operation do I do with the powers? No. Multiplication. So that becomes e to the 4x. Sorry, that was kind of... Here, what you're thinking of, when we're multiplying 2 terms with the same base, then we add the powers, yep, and that becomes 4x plus x squared. And now I have each side written with the same base, which is what we were doing like with the earlier exponential ones. We had to like kind of rewrite them with the same base, and then I can set the powers equal to each other. This one, I have a set the factor to solve. This one's quick and easy to factor, 6 and -2. Giving me solutions of -6 and +2. Okay, so there's just kind of some properties. Again, eventually, folks, we'll be able to like algebraically solve these equations. But when they're set up like this, just use some logic. We know an equation means each side's equal to each other, and if they have the same base, then you can set the powers equal to each other. Now, I know you're all wondering, well, what if we had something like this? When I don't have something that's written with the base e. Don't worry. There's ways to solve this, and we'll get there eventually. But for now, anytime you're asked to solve something, it will be able to be written with the same base on each side, set the powers equal to each other. Anyone tried any of the homework ones yet?
No.
Saving them.
I almost did.
Same for
I did very good.
Okay, the only last thing we have to talk about, application problems. So I kind of mentioned like exponential growth does occur naturally a lot. Like I talked about the coronavirus, and I was actually trying to find like an actual graph. And I found one back in like when COVID first hit, like in March of 2020, how it like kind of like grew exponentially, I think before everything shut down or whatever. And it was a curve. If we have time, I'll pull it up. But it was a curve that, like the numbers were pretty low. And then by like March 2020, they had like shot up like that. So it was like a pretty true exponential curve. Now, hardly ever like do we have perfect linear models or perfect exponential models in real life applications, but a common application with exponential growth and decay is compound interest. So those of you that like have some type of like savings or like bank account know what interest is. Kind of. Basically, it's like the money the bank pays you for like keeping your money in your account. Okay, so when you go, let's say you're 5 years old and you got a $500 check from grandma for your birthday, and you put that $500 in a savings account, and then you don't touch it, but you leave the money in there, you don't take any out, you don't withdraw any, or you don't put any more in. Eventually, like in 10 years, when you go to check that balance, like there'll be more than $500 on there because the bank uses an exponential like model to calculate and give you money called interest for keeping your money deposited in an account. So if you take out a loan, if you're borrowing money from the bank, interest can be bad because so when I bought a car like 5 years ago, I was like shopping around because I needed a loan because I didn't have the money to just buy a car. I was shopping around for very low interest rates because now if it's money you're borrowing, that interest is going to build up on your loan and you end up having to pay more than what you actually borrowed. If that kind of makes sense. Heard of interest?
Yeah.
Yeah. Okay, great. So here's the exponential like model piece. You've maybe seen this formula before. I don't know. We do it kind of in Algebra 1 and Algebra 2, but you have they use A to stand for like the balance in your account. And you have whatever your principal is, that's the money you put in. Now here's the exponential piece, and you can see how this is kind of related to E, and that's actually how Leonard Euler discovered this. He was working with a guy that was studying compound interest. Is how he discovered this number. So it's 1 plus, and then I'll change colors. R over N. And here's where it becomes exponential to the power of N times T. So you don't really have to like derive this equation. You just have to memorize it or know where it is. But I'll kind of explain why this works. So A is obviously like the balance that you're going to have or your amount in account. So what it does is it factors in how much you have in your account. So if it's that $500 check from grandma, it factors in R, whatever the interest rate is. Now, normally the rate's given to you in a percent. And in order for this formula to work, it has to be in decimal form. Okay, so instead of plugging in 4%, it'd be 0.04, right? We'll practice some. And then N is our number of times it's compounded per year, because your interest rate can be compounded annually, 1 time per year, semi-annually, twice a year, monthly, 12 times a year, and that factors that in as well. And then obviously also how long you leave your money in the account is going to affect how much your balance is after whatever the time period is. Okay, have you seen this formula before?
No.
Really? Oh, this is so fun. Okay, great.
What is
I
it?
should start counting how many things are fun.
Well, the limit does not exist. Okay, so let's think of a really basic example. Let's say I let you borrow $1 and I said, I'm going to give you a deal, 100% interest rate, but I'm only going to charge you annually, so once a year.
Nope. I'm out.
So after a whole year, you would owe me the dollar you borrowed plus 100%. You would owe me now $2. Okay. What if I said though, I'm gonna give you a deal. I'll give you only 50%, but it's semi-annually. So I'm gonna calculate in the interest now every 6 months. Let's see if this would be a better deal. So we have the $1 that you borrowed. So 6 months pass, and 50% of a dollar is how much? 50 cents. So now you owe me $1.50. And then the next time I say I'm going to charge you 50% of this, which is 75 cents. Now you owe me, even more. So sometimes interest can start compounding on itself. So it would have been better for you to take the 100% interest for the full year instead of me calculating after 6 months. Now your new principal or your new balance is $1.50, and now after a year you owe me $2.25. Okay, and we could even take that further. What if I calculated and said, all right, how about 10% every week?
No,
We could count it 52 times
no thanks.
to see how much it would be after a year. But that's where this formula comes from. Like it factors in, n is your number of times it's compounded in a year. So you take your rate, let's say it's 52. If it's compounded weekly, you take your rate, you divide it by 52. Okay, raise it to the power of 52 times in 6 years. So 52 times 6, that'd be how many times it's compounded. So obviously, the more times it's compounded, and this is where Euler's number comes in. I'll go back to that. See how it's kind of similar to this? And we talked about as this number got really, really large, it approached this E, this irrational number. And that's what plays in. And as I mentioned, that's how this was discovered, this number. If you just continually keep compounding it, so you're like, okay, what if I compound it every single minute in a year, or every single second, or every single nanosecond, or compounding continuously? It comes into using our natural base, a special formula that allows you to continuously compound it and calculate all those calculations. So the more times it's compounded, the more interest you earn if it's money you're saving, or the more interest you'll pay if it's money you're loaning. Okay, so what you need to know is, and I kind of listed this out for you. P is the principal, money you're putting in. Okay. R is our rate. N is the number of times it's compounded per year. T is our time in years. If you see that it's compounded continuously, that means this number of times compounded is growing infinitely. So then we use our natural base. So our principal times E to the power of the rate times T. PERT, that's how I like to call it. A is the balance, P is the principal, R is the annual interest rate, T is the time in years. All right, now I picked a problem where we'll calculate it quarterly, monthly, continuously. So just remember, N is the number in each year. So if it's daily, how many days are in a year?
365.
Beautiful. Monthly?
Well,
Weekly?
52.
52, yep. Semi-annually would be 2. Okay. Annually would obviously be 1. Quarterly? 4. Yep. Those are usually the most common ones. Okay, so let's try one. Let's say I just got a stipend of $12,000, and I was like, ooh, I better save this. So I'm going to put it in an account, and they're giving me an annual rate of 3%. That's really high. That's great. Find a balance after 5 years for each type of compounding. So each kind of period in a year. Compounding period is kind of what it's called. So if it was quarterly, that means our number of times compounded is 4. So we're going to use this formula. Okay, this obviously exponential function here. P is my principal, or my amount that I deposited, which was $12,000. So I'm going to take my $12,000. And now obviously this piece is going to kind of calculate in that exponential growth of the interest and multiply it to the 12,000 and factor in how much interest we're earning. So 1 plus, my rate was 3%. Don't forget to change that as a decimal. That'd be 0.03. Now the reason I have to divide that number by 4 is because I'm compounding this quarterly. So I gotta divide that by 4. That's how much the percent, because they gave me the annual interest rate. Okay, that's gonna factor my interest, and then this is gonna exponentially grow to however many times it's being compounded each year, 4 times how many years you're leaving this in, which is 5 years. Okay, we do need to practice typing this in our calculator because I'll show you an easy way to do this. So follow along in your calculatrice with me. Okay, we got to start within the parentheses. So I always do like the rate, 0.03, divided by the number of times compounded first. So that's how much percent it would be when I compounded it at each quarter, right? 3% annually divided by 4. All right, then I always add the 1. Obviously, order of operations. We got to start within the parentheses, add the 1. So there's kind of like my exponential growth factor. I'm going to raise this to, so you're going to hit the up arrow. And guys, if you keep just doing this, it'll just keep feeding the answers. You don't have to retype 1.0075. In parentheses, my number of times it's compounded, 4 times however many years, 5, which is really going to calculate it 20 times, right? If you're compounding it quarterly in 5 years, it'd be 20. Hit enter. Okay, there's kind of like the interest now calculated into it. So now we got to multiply it by whatever the principal is to factor in how much was actually deposited, $12,000. That's how much would be in my account after 5 years if I didn't take any money out or didn't put any money in. $13,934.21. Obviously, we're going to round to the nearest penny when we're talking about money. Wow. So how much of your balance there was interest? Well, obviously, almost $2,000, right? $1,934.21. That was just interest. Interest is never that high. I get too excited. Okay. What if we were to compound it monthly? How many times would I calculate my interest then? In a year? 12. So again, I'm going to use this formula. $12,000 is still my principal. So 1 plus my rate is still 3% annually. So I'm going to have to divide that by 12. And the reason why you have to add 1 to it is because basically like in exponential growth, the base is always 1 plus whatever the rate is, and that would make your base like an exponential growth piece, and we're changing it like a decimal. All right, to the power of, I'm compounding this 12 times for 5 years. So total is 60 times. All right, I'm gonna walk you through the calculator one more time. Start with the rate, 0.03. Now we're dividing it by the 12 times it's being compounded. Add 1. There's your exponential growth factor. So I'm going to raise that to the power of 12 times 5. Now, I know you can obviously do that in your head, but sometimes I honestly just type it so I don't even have to like worry about making a mistake with math. And then now I'm going to times that by my principal. $13,939.40. And we just talked about like the more times you compound it, the more you're going to earn, right? So that makes sense that we got a bigger number. It wasn't that much bigger, right? Yeah, about $5 more. I'm just using approximating because I'm obviously rounding this, but okay. So when you're doing these problems too, like keep in mind, the more times you're compounding it, the higher your balance should be in the end. Now, compounding continuously, such as this number gets infinitely large, that's our special formula, that's PERT. That's using our natural base. So I'm going to need to use this formula. That's the only time you use PERT is if you see that it's being compounded continuously, or continuously being compounded is another way it's phrased. So we take our principal, $12,000. That perfect base E, that irrational number, will calculate in the continuously compounded. Now, this one's a little bit different. This time you raise it to the power of the rate, because we still have to factor in the rate. 0.03. Times my number of years, which is 5. All right, now this one, because everything's being multiplied together, you can really type this all in 1 in your calculator, okay, especially using now that you know how to use that E button, obviously, but you don't have to worry about order of operations. You can just do 12,000 e to the power of, in parentheses, 0.03 times 5, close parentheses. Okay. And again, the more times we compound it, the higher our balance should be. So this answer makes sense. $13,942.01. Again, it's not like a huge difference. I mean, you could do it daily, see what you get, but that's just a really common exponential application problem, and also a good application to when that Euler's number is used in real life. Okay, that's a wrap on the notes. I'm gonna stop the video.